Okay, we're still in chapter 12 and we're looking at properties and behaviors of gases. And this is the second video. In this video, we're going to be looking at some of the properties that we can measure for a gas. And we're going to start with gas pressure. So all gases, we need to know that all gases have a certain pressure that we can measure. So what is gas pressure? You probably know what pressure is, but if you don't, we'll go ahead and define pressure. Pressure, you might have learned in a physics or intro to physics class, is force per unit area exerted against a surface. So the pressure that anything is exerted is always force divided by area. What does that mean? Well, I'll give you an example. Let's say that I have two surfaces here. And they have the same area or surface area that I've drawn, we'll just assume. So in this same amount of area, we're going to look at the force, the total force that is exerted. Let's say I have a gas inside of a container, I'm just showing a close-up, that's very confined on the right, and a gas that's less confined on the left. Alright, all of these particles, let's say, are moving at the same kinetic energy or the same rate. They're the same type of particles, but one of the particles at a higher pressure than the other, which means that the particles are very confined and they're placing a lot more force on this unit area in one of the examples versus the other. So if all of the particles are moving at the same force or hit or collide with the same force, we can measure the force of the collision here, and we can just call it like 4 newtons or something. We'll just keep it simple. On the right hand side, in that same unit of area, let's say all of these particles are hitting the wall at the same time. They're all colliding. Here we have about 4 particles colliding in that area, so that if they were all at 1 newton force, we would say 4 newtons per let's say square inch. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 newtons per square inch. We would say that this on the right was at a higher pressure than this gas over here because there's more force per unit area being pushed against that container or the side of that container, that surface. So gases have pressure because we know, there's an example of gas in a balloon, those particles are moving at high rates, they're moving at high kinetic energies, and they're pushing against the walls of the container. So when we measure the pressure of a gas, and you've probably done that before if you've ever measured the pressure of your tire with one of the tire gauges, you notice how the gauge, when it measures, it pushes out the end of the gauge. Well, the particles inside of the tire, for instance, are literally pushing on the gauge, and that measures the force per unit area. And so that's what gas pressure is. It's the particles colliding against the walls of the container, the force per unit area they do that. You've probably heard of the term atmospheric pressure too. What in the world is atmospheric pressure? Well, it's the pressure exerted by the gases in the atmosphere. So let's say, I'm going to just draw this quickly, so it's not a good drawing, but let's say you have the Earth here. Here we've got the Earth. We're going to draw some continents, okay? Got over here. I'm not going to get big with that, but let's say we have the planet Earth. The atmosphere consists of a homogeneous mixture of gases, oxygen, nitrogen, a little bit of helium, argon, a little bit of carbon dioxide, some water. So there's all these different gases that are in the atmosphere. And those, I'm going to make them really big here, just as in a point, but those gases are in the atmosphere above the Earth. And so those gases move randomly in the atmosphere in all directions, straight lines. And they move with a certain force, mass times acceleration. When those particles collide against the surface of the Earth, they exhibit a certain amount of force. They incur a certain amount of force against the surface of the Earth. If you divide the force of the atmospheric gas divided by the area of the Earth, you get the pressure the atmosphere exerts onto the Earth. So this is called the atmospheric pressure. Now, the atmospheric pressure, I'm going to kind of look at a side view of the Earth now. Here's the desert, like the Mojave Desert, and you've got the Rocky Mountains. Then you've got the sea down here. I'm just kind of giving you an example. We know that when you look at the earth, the surface of the earth is not flat, right? So on the surface of the earth, we have mountain ranges where the surface is higher. We have flat places like here in Florida, very, very flat. We're right around sea level, right? So sea level. And then you've got under the sea, you've got things that are lower if you look at the earth in the solid phase. So we know we have high and low portions. Well, why am I even talking about that? Because the atmosphere is contained within a certain region around the Earth's surface, right? And so we have all these atmospheric gases trapped inside of our atmosphere, and they exhibit different pressures at higher and lower points on the Earth. At the higher points, there's less distance between the top atmosphere and, let's say, a mountain. So there's less force being exerted onto the mountains because there's less particles per unit area exerting that force overall. However, when you get down to around sea level, there's more particles here, all right, and they're all exhibiting a certain force, and there's an overall weight. There's more atmospheric pressure at sea level than there is at the mountains. So we know the atmospheric pressure varies. You can actually be in like a canyon, like the Grand Canyon. You get low, below sea level, and there you even have a higher pressure. So the atmospheric pressure can vary. You've probably heard the term at sea level before, and that the sea level is kind of where we measure the general atmospheric pressure. And at sea level, if we talk about in units of atmospheres, which is atmospheric pressure, the atmospheric pressure is generally about 1 atmosphere, ATM being a unit of pressure. Is this the only unit of pressure we have? No. In your book, you read about others. We have the atmosphere, 1 ATM, and 1 atmosphere of pressure equals 760 millimeters of mercury. You can read about where that came from in your book, but that's just another unit. So 1 atmosphere is 760 milliliters of mercury. That turns out to be a conversion factor, and we're going to use that in a second. Another unit is the torr. So we have the unit torr for pressure too. And a torr is basically the same thing as a millimeter of mercury. So 1 atmosphere is 760 millimeters of mercury. 1 atmosphere is also 760 torr. So if you put that together then, how do the torr and the millimeters of mercury compare to one another? Well, it turns out that 1 millimeter of mercury is the same pressure as 1 torr. So they have the same numbers but different units when you convert them. If I said, how many millimeters of mercury is 70 torr? Well, it's 70 millimeters of mercury. Okay? So we have different pressure units that we can use. You've probably heard of things like PSI, pressure per square inch. There's also something called the Pascal. A Pascal is a PA. That's the unit that's used for Pascal. And 1 atmosphere is 101,325 pascals. So we have several different units that we can use for talking and discussing pressure. Now, there's a special pressure, and I'm going to talk about temperature at the same time, that you need to know. And so most chemists, when they run reactions, there's a standard temperature and there's a standard pressure that chemists or scientists will use when dealing with gases. And we call this the standard temperature and pressure conditions. So the abbreviation for these conditions are STP, standard temperature and pressure. So what is the standard temperature and what's the standard pressure? The standard temperature of a gas is about 273 Kelvin, or it is 273 Kelvin, or 0 degrees Celsius. So 273 Kelvin, or 0 degrees Celsius. What is the standard pressure we work at? Well, it's sea level. It's 1 atmosphere of pressure. 1 atmosphere of pressure is our standard pressure. that equals 760 torr, 760 millimeters of mercury, or 101,325 pascals, but 1 atmosphere of pressure. So if I ever tell you I do a reaction at STP, I'm giving you the temperature and I'm giving you the pressure conditions that gas was under. 273 Kelvin, 1 atmosphere. Know what STP is, okay? Let's practice doing some conversions from one pressure to another. Alright, so it's our first pressure conversion problem. Let's look at it. We've done a lot of conversions, haven't we, in Chapter 7 and Chapter 9, so we're not away from it yet. Okay, let's look at the first one. It says convert 675 millimeters of mercury to atmospheres. So we're given 675 millimeters of mercury. We need to convert that to atmospheres, so how are we going to do that? Well, we want to get rid of millimeters of mercury, so we're going to put millimeters of mercury in the denominator. We want to convert to atmospheres, so we're going to put that unit in the numerator. Now we're going to add our conversion factor numbers. So we know, I mentioned above, that 1 atmosphere equals 760 millimeters of mercury. So basically what I'm doing here is I'm canceling out the millimeters of mercury and I'm getting us to atmospheres. So we set it up. What is 675 divided by 760? If you do that in your calculator, the answer I get is 0.888, 3 significant figures, atmospheres. So 675 millimeters of mercury converted to atmospheres using the conversion factor we just talked about is 0.888 atmospheres. Alright, that sounds about right, because 1 atmosphere is 760. It's a little less than 760, so it's a little less than an atmosphere. So always make sure your answer makes sense. You don't want to make it not make sense. Okay. Alright, so let's do the next one. So the magic number is there that if you're converting to ATM, divide by 760. Okay, let's convert from millimeters of mercury to torr. If you have 675 millimeters of mercury, how many torr is that? This is an easy conversion. 675 millimeters of mercury is 675 torr, because we just said above that 1 millimeter of mercury is 1 torr. So those should be the same. Alright. Now, we're going to be doing a lot of problems in the next video that relate pressure with other variables. Pressure is not the only thing that we can measure or identify for a gas. If you have a gas, you can identify the pressure of the gas by measurement. You can measure the volume of the gas. You can count how many moles of the gas there are. By the way, N equals moles. We haven't seen that yet, but in equation mode, I don't know why I put an equals there. Somebody forgive me quickly. Alright, so we've got pressure of a gas that we can measure. We've got volume of a gas we can measure. We've got the moles of a gas we can measure. We can also measure the temperature of a gas, right? Using a thermometer. Stick it inside of a gas. Oh, it's hot. It's not that hot. And what else can we measure? Let's see. That's pretty much it. Okay, that's all we'll be doing. So we can measure pressure, volume, moles, that's a new one, N for moles, and the temperature, we always use Kelvin as our temperature units, of a gas. And it turns out that all of these variables of a gas are related. So if you have a certain amount of moles of gas molecules, if you change the number of moles of your gas and keep everything else, try to keep everything else constant, other variables will actually change. One affects the other. Here I say that pressure depends on several things. The pressure of a gas depends on how much of the gas you have, how many moles of the gas. The pressure also depends on the temperature of the gas. Because remember, pressure is force per unit area. So if you're at a higher temperature, a higher kinetic energy, you're going to have a higher pressure, right? So pressure depends on the moles of a gas, the temperature of a gas, and pressure also depends on the volume of the gas. We used that example earlier with the piston. If you have a smaller container, or you decrease the size of the container, the force per unit area is going to be much greater. So the there's pressure-volume relationships, there's pressure-mole relationships. There's pressure-temperature relationships. We're also going to find in this chapter that there's also volume-mole relationships. There's also volume and temperature relationships. So all of these variables, when it comes to a gas, are interconnected. And we're going to learn about how these variables affect one another when you change one. That is, you don't keep something constant. So that's what we're going to look at next, in the next video.